All right, first office hour. So as I mentioned in the Slack channel, a couple things I want to go through today. First, a little bit of automating the modeling process, and also just like a recap on the main differences on how we use stats models versus scikit-learn, because they both overlap a lot, but each have their own like different quirks, I guess. So how my advice on how to efficiently use both of them together. Including like dealing with train test split and all that. I'm also going to talk about some scripting functions, which can help to streamline your notebook. I will say for scripting this project, I'm not going to make it mandatory to do that, but next project it will be. So feel free to chat for this project, but I'm not expecting that. Although during our project review, I will point out places where I think can be automated. And finally, I'm just going to talk a little bit about actually, I'll save the presentation talk for next one, just in case. I think I have something else on this notebook that might be a little bit more helpful. I'll talk about like making a couple of visualizations. Yeah, okay, we'll do that. Okay, so to start, I want to talk about the differences between stats models and scikit-learn. So here I'm using, and I've already run this code, so I don't have to run it as we're talking. But we're using our usual miles per gallon data set, and we are trying to predict miles per gallon with these features, just as an example. So remember, this is our syntax for running the OLS and stats models. As you can see, not a perfect regression yet, but this is just procedural code, just to walk through how it's done. And here we have our model built. Our model is stored here in the variable called model. So this is how we do it in stats models. As you can see, maybe not the, it's helpful in the sense that we can see our p-values, you can see our coefficients, that's all great. But when it comes to things like train test split or cross-validation, it is actually harder to do it in stats models versus scikit-learn. So just really quickly, here's how we do it in scikit-learn instead. So this code is quite similar to what we saw before. We're instantiating our model here. We're doing a train test split first, and then we're fitting our model on our train set. And then you can see here, we are doing our train, we're predicting on our train and test set to get the predicted values, and we're going to compare those errors. So within scikit-learn, we have these built-in methods for calculating our metrics. So for example, we have R squared, which the default scoring for a linear regression model is just R squared. So if you do dot score, and we'll actually see this for some different models next phase, different models have different default scoring, and the default scoring for linear regression. Let me pull up the documentation so we can see what that looks like. So this is the linear regression documentation. And if you scroll down to score here, you can see that there are these methods. The dot score will basically give you the coefficient of determination, the R square of the prediction. So that's the metric for that. Other models we'll see next phase that they have different metrics, and they'll actually tell you what it is here. And as you can see here, dot fit is a method, dot predict is also a method. So those are the ones that we've used. So here you can see that we're using the dot score for our R squared. And then we're using mean squared error, and then taking the square root to get the root mean squared error for our train and test set as well. So quick differences between R squared and Rmse. R squared is sort of a goodness of fit metric. The regular definition is how many percent of your target variable variation is explained by the features. But it is truly a goodness of fit metric. Like how well does your line fit your data, which is kind of similar in some senses, but also completely different from Rmse, which Rmse is a measure of how well it is as predicting, how well your model is at predicting values. So as you can see here, our train R squared, we explain 72% of the variation in your miles per gallon with all of those other features in your train set. And for your test set, that's a 64%. But in this case, you can actually definitively say for your train set, your average error is about 4.17 miles per gallon off, and for your test set is 4.4 miles per gallon off. So it is actually very, very common that your test metrics always perform a little bit worse than your train metric. And the idea behind that is just because your model is being trained on your training data, not your test data. Your test data is actually data that your model has not even seen. So the fact that these numbers are decently close to each other is not bad. It's pretty good. And again, always interpret these numbers in context. So in this case, these 4.17 and 4.4 numbers, these are miles per gallons. I don't know anything about cars, but in your projects, hopefully you'll do a little bit of research or have some benchmark numbers to compare that to. Like, let's say you're doing like your housing price model and your RMSE ends up being like 2 million. That, I think, for predicting prices is not good. If you're $2 million off for the prediction of a house, that is not good. So do interpret that in context. Now, since we're talking about Scikit-Learn, Scikit-Learn also has some attributes from your model. So for example, let me show you where that is on your here. So attributes of your model, you have coefficients, rank, and singular, not important, but coefficients and intercept. So even though on Scikit-Learn we don't have, those p-values that we have here, we can still obtain our coefficients if we want. So the way that you do that is linreg.coef, and these are actually the coefficients that should correspond to what we have here, right? So let me see if I can fit them all on the same page. We have, oh, sorry. It's not exactly the same because this is on train test split and that isn't, but they're kind of similar. They're all in the 0.0 values and those should match up. Okay, so if you wanted to use train test split on your for stats models, you can do that as well. So let me just quickly throw it over here. The formula should stay the same. Formula is here. Your model is here. And instead of the data being your, instead of your data being data, we're just going to use X train as our data. Oops, oh, damn. Miles per gallon is not defined. Oh, sorry about that. Let me show you all something really quick as well. If you want to do a train test split with without X and Y being separate, you can actually do that as well. You can do data, and then you can have train and test. And that works. And then your data can be on your train just like that. So that's another way to do it. And as you can see here, this result of the train has my miles per gallon with the X features, and same with the test. So just in case you wanted to use stats models more, you can do it this way as well. And I believe our curriculum doesn't actually show this method of doing train test split, but just so you know, that can be done. So anyways, now that we have this and our stats model is fit on our train set, we can actually do model.predict. And remember, model is our stats models model and linreg is the scikit-learn one. We can do model.predict on our test and you can get your values here. So you can sort of use both to do all the procedures. I mean, you can use stats models to also do train test split procedures, but just in case you wanted to do a slightly different workflow than what I'm showing you, you can do that as well. Questions about that? I know that was kind of like a lot of confusing code all at once.
So just to be clear, we can use either, do we have to use both stats model and scikit-learn, or we can use either one?
You can use either one. I will say I do recommend using both, and I'll actually show you a function where I'm using both. So yeah, I do recommend using both, but you can use, I would say if you were to pick one, I would pick stats models just because it is important for this project to see this output and evaluate your model that way.
Thank you.
You're welcome. And yeah, so with this test over here, sorry, not this, with this predict test, you can just compare that to your test miles per gallon, compare these results, and then you can get your root mean squared error. So I believe you can do like a test MPG minus model.predict test, take the square of this, yeah, square of that, and then that should give you all the squared. And then you want to divide that by 79 because there's 79, oops. Oh, you want to take the sum of that divided by 79 and then take the square root of that. And that will be, oops, that will be your overall root mean squared error. This is a very poor way of doing it, but if you wanted to calculate your RMSE, that's how you can do it as well. You'll see here that this value here is different from this, and that's because we're using a different train test split. I am going to talk about using the same train test split for both stats models and scikit-learn, like right now, but are there any questions about either of these procedures separately first? Okay, awesome. If at any point y'all have any questions, you can just interrupt me. Okay, so what I did here, and what I do recommend working on, maybe not for this project if you don't feel like very comfortable with all of these linear regression concepts yet, that's completely fine. But I would like you all to start thinking about automating your code a little bit more. As you know, this project is going to be running a bunch of linear regressions over and over again. Yes, I said 4 steps, so most people end up just running more, making very small changes with each one. So you're going to be running a lot of the same processes over and over again, just with maybe like different subsets of your data, different parameters in your, or different parameters for your linear regression, so on and so forth. So I do recommend that if you feel up to it, create a function that does it for you. This is an example. I would say feel free to use it if you'd like. It is available on your study group repo, but I will say that if you are going to use it, one will have to change the data set that it's using, but also make sure that you understand what this function is doing. And I'm going to talk about it in a little bit. So what this function is essentially doing is I'm having this function take in different train and test data, or just take in train and test data as arguments, and running both stats models and scikit-learn. So first, what I'm doing is I am running my stats models over here. So because I'm feeding in the train and the test separately, I'm actually putting it back together here. And then I'm using my regular OLS formula, exactly the same code as what we saw before. And then I'm doing the same process on scikit-learn. And I'm doing this in scikit-learn just because I personally like using their metrics more. I just think it's, it's already built in. So I like using their metrics more, therefore I'm using the code here. So with this function that I call model, I'm running the same model out of 2 libraries, 1 time each, and getting the relevant metrics out of each one. So from here, I get my train and test R squared and Rmse, and you can see this is an output. My train and test Rmse and R squared, as well as the stats models output, because you can see here, I'm returning the model.summary and printing these as well. So just by running this one line, I get my R squared, my Rmse values, and this output that I can then I can just reuse this this function, this line over and over again with different subsets of data. So just as an example, let's just say I want to drop those high p values. So here I'm going to drop displacement, cylinders, acceleration, and displacement, as you can see here, because they have high p values. I'm going to drop those. This is not how you're going to do it, but just really quickly, I'm going to drop these, redo a train test split, and then rerun my modeling function. And with rerunning my modeling function, you can see that hopefully there's some improvement. Let me see. So it starts from an RMSE of 4.17 and 4.4. Here, when I run it, 4.17 and 4.43. So it seems like it got a little bit worse, but however, at least my p-values are all significant. So yeah, and again, to get all of this output, I just have to run this one line now because I wrote that function at the start. This is a good point to also talk about. If you're trying to decide between having better metrics or having a more significant model, I would say prioritize having a more significant model, because having a more significant model makes it more reliable. It just makes it more reliable as a model as a whole, because these metrics can be kind of sensitive to your different train test splits, right? I think that if I were to just rerun this, the numbers are going to change. Oops. Oh no, what happened there? Okay, let's pretend. All right, not a big deal. The idea here is if I were to rerun these over and over again, the numbers keep changing. So you can see here, the train R squared keeps changing. Okay, any questions about that? I don't know why that didn't work. Cool, okay. I would say for a function like this, you're going to definitely be writing this for your next project. Like I'm going to make sure all of you write this function for your next project, and it'll be slightly different, but same procedure as well. So if you want to use this, feel free to adapt it for your own, although mine for some reason did not work. I don't know why. But yeah, any questions about this, more than happy to talk about it. Okay, questions at this point? Cool. All right, so the next thing I want to talk about is scripting. So the idea of scripting sort of comes after you get used to writing functions. So as we get deeper and deeper into this course, and we're already almost halfway through, as we get deeper and deeper into this course, you're going to be writing a lot more procedures, and you're going to be writing things that you're going to have to do over and over again. Very similar to this project, how you're doing the same modeling procedure over and over again, just with different like subsets of features or different transformations of features, for example. So having a function like this is extremely useful. But but imagine this project where you have maybe like 10, 20 different functions that you're using, because you can use functions for like your data cleaning, for even your transformation code, your modeling, your evaluation. Those can all be written in functions, and that can really start to clutter your notebook. And because of that, I would suggest while you're writing functions, also get used to the idea of scripting. And scripting is something that we don't really have in our curriculum, but is something that we always talk about. And it's basically importing functions from Python files. So what I have here is I created a Python file called functions.py. And as you can see in functions.py, I actually imported all of my libraries, as well as I copy and pasted the function that I had earlier over as well. So this is something you can do. Pretty much, I would say, test your function in your Jupyter notebook to make sure that it works. And after you're absolutely certain that this function works, and in my case, I guess it doesn't work over here. I don't know what's going on here. Once you're completely sure that it works, you can just copy and paste it into a Python file. And the way that you can create a Python file, several ways to do it. One, you can use like your Visual Studio Code, or what's another one? PyCharm or Atom, or any sort of code text editor to do that. Or you can honestly do it directly in Jupyter as well. So in this Jupyter homepage, what you can do is just click a new file, and instead of Python 3 notebook, do a text file. And when you do a text file, just name it something. I'm going to here call it functions2, and always end it with a .py, and py just stands for Python. And once that's done, you can copy and paste whatever you want. So let me just, as an example, I can define a function called double. And let's just say I want to double a number, and I return the number times 2. And that's my function, just as an example. So in here, what I can do then, and I'm just going to do a quick example, I can say from functions2 import double. There. And now that is imported, I can actually use my function. I can double any number I want. And that's a function that I wrote. I wrote my own custom function that I imported. So similarly, you can do that for your modeling function. So here I'm importing model, and you can also alias this. You know how when we do like import pandas as PD or import numpy as NP, we can do the same thing for our function, so we don't have to write the whole name of it in case you ever wanted to do that. So here I'm importing model as M, and I hope this runs. Okay, cool. That did run. Okay, so I'm importing model as M, just so you know it's not the same as the function I wrote before. And here I do my same train test split, and I just use my M function, throw in my train test, and I have my results over here. And so that is me using a Python function from a script. So this file is now called a script. Any questions about this part? Cool. So I would say this really does streamline your notebook. As you can see, like if I didn't have this function, whether I had it in a script or not, just defining this function meant that I did not have to copy and paste like these, I don't know, these like at least 8 lines of code over and over again for every model that I run, just to see my metrics. So yeah, highly recommend. And if you have any questions or any difficulties on setting this up, you can let me know.
I have a question real quick.
Yeah.
Since we use a lot of the what's it called? The learning app from the Flatiron
Oh,
website.
the Learn environment.
Yeah. We would, how would you import your own functions onto that environment?
Okay. So they're kind of separate things. The
Okay.
environment basically defines what versions of packages you're using. And these scripts, as you can see in these scripts, I'm importing those packages as well. So these scripts can still run in Learn environment, or if you choose not to be in the Learn environment, it doesn't matter. So if you were to run this script in the Learn environment, it will run in like those versions that are defined in the Learn environment. If you decided to run it like on a brand new computer, for example, it'll run in like Python 3.9. So they're kind of independent things. And a script, if it's written in something that's kind of like version agnostic, it should be able to run fine.
Okay. So I was actually trying to aim towards a LumaDesk. I just saw the name.
Oh, okay. In Illumidesk, that's a little trickier because if you wanted to, let's say you wrote like a bunch of custom functions and you wanted it to, let's say you wanted to, is the idea here you want to import them in your Illumidesk?
Yeah, because I usually just work off of those.
Oh, that's a good point. I actually think, I'm actually not sure. Let me, if you don't mind, I'm gonna just quickly try it out. I think that you can do the same thing. Amir, you're gonna say something?
Yeah, you can do the same thing. Because
Nice.
that's what I did when I started the first project. I was working off of the lectures, but like it's localized to that instance in the notebook that
Yeah.
it's working off of. So it got kind of confusing when I was trying to get it out, because when we had to move it over to what's it called?
Oh, like a
Blinking.
repo?
Yeah, like a GitHub repo. Then like me moving it out, me personally, I was just confused because I was like, okay, where is it? And then I was like hunting through
Yeah.
the lectures, trying to like figure out where it was, and then what I was using, because then it's cluttered with the data that's from the project, like from the lesson plans too.
Yeah. Okay. So I guess we can segue just or tangent super quickly. For Illumidesk, if you want to do this in Illumidesk, you could do this here. But to get to this page, you have to go to Illumidesk from the side panel. Because if you go directly from a lab, it will open this directly without bringing you to the side panel. And so once you get to this side panel, when you click it through the side panel, it brings you to this page here, and you can create a new file here. It'll be a little trickier to get to the file because I guess it doesn't really matter so much, because let's say you find whatever you're working on. Let's say I'm working on this one. I guess you can just, you could create like a text file, a Python file in there, and that should work fine. Well, I personally don't use Illumidesk myself, so I'm glad that we talked about this.
Okay, thank you. I'll try it out for future reference. Thanks.
Cool. Yeah. Any difficulty with that, feel free to let me know. Any other questions at this point? Okay. The next thing that I wanted to talk about, and I don't know how long this will take, so hopefully not too long, is checking the assumptions, because I know that was something that was a little bit hand wavy when we were talking through them, because there was just a lot of material to cover in like the 1 week that we actually talked about regression. So I have some advice for checking for assumptions that I have in this notebook as well. So remember that there are 4 main assumptions that we have with regards to multiple regression. 2 of them come before you model, and 2 of them come after you model, or 2 of them you can check for before model, but you can keep checking for them after, and then 2 come after. 2 of them are a result of your modeling. So the first, actually, let me just type them out since we're here. So the first, we have the linearity assumption, and second, we have the multi-collinearity assumption. So these are the 2 that you can kind of check through your EDA. Linearity, remember, it is, are your x's correlated with your y? Are your features correlated with your target? And you do want them to be correlated. So you want features to each be correlated with target. And that's something that you can check for in your EDA, run some correlation coefficients, throw some scatter plots on there. And also multicollinearity. You don't want features to be correlated with each other because that causes high p-values, causes redundancies in your model as well. So correlated with each other. So these are the two that you can sort of check through your EDA process, which is nice. You don't have to run any models. However, the other two assumptions, now those only you can check for after you model, and those are homoscedasticity, and also normality. And so those two you check for after you model. And to go through what these are, normality is you want residuals to be normally distributed. And homoscedasticity is you want residuals to have equal variance or consistent variance. And those are important to check for because only if all your assumptions are fulfilled, then you have a reliable linear model. Because a lot of how the linear model is constructed and how it is fit does depend on these assumptions holding true. So we'll go through some of the things that you can do to check for these assumptions. So first we have our regular regression here again. And let's talk about normality and homoscedasticity, because the first two you can pretty much do through a bunch of scatter plots in your EDA. So let's talk about the second two. So we're going to run this regression real quick. Same thing that we've been doing. And then we're going to look at residuals. So when you do it through stats models, model.resid actually gives you your residuals straight up. So in this case, this model, I did not do a train test split here. You should do a train test split, but because I didn't do a train test split here, I know there's 392 data points here. Model.resid gives me the residuals for the 392 data points, literally the error between your predicted and your actuals. So you can actually see that here. If you remember, model.predict is how you use the prediction function for stats models, and you have those over here. And what I have over here is y.values.flatten, and I'll sort of talk about why I did that. Y.values.flatten. So what is y? Y is our miles per gallon column. In order to compare the two, it's just easier to have them in the same format because model.predictx is model.predictx is an array as well, or in a series, which I guess same thing. Not the same thing, but it's in a series, it's a one-dimensional series. Why I do y.values.flatten is actually pretty interesting. So y looks like this, right? Y looks like this. If I do y.values, it actually looks like this. And you can see this shape-wise looks completely different from the .flatten. If I do a y.values.shape, it's 392, 1. I'm going to explain what .flatten does in a little bit, but when I do .shape here, you see it's 392, which I think seems like it's the same thing, but it's actually the difference between a 2-dimensional array and a 1-dimensional array. So here, this .flatten .shape, this is 1-dimensional, whereas this is 2-dimensional, which is something that's actually, it does come up sometimes if you try and use a .predict function, you don't have it flattened in the right way. When you do a .flatten, what it does is it turns into a 1D array. So let me just take away these .shapes. Y.values, you can see it's basically like 392 nested 1-element lists in a single list. And when I .flatten it, it all flattens out into one list itself. So that's why you have to do .flatten in this instance. And literally the difference between the two, the differences between y and model.predict is equivalent to your model.resid. So if I actually do the actuals here minus model.predict, you can see that these match. 0.95, 1.18, negative 0.95, 1.18. So these are the same thing. So cool. Now that we know what our residuals are, we have to check for the assumptions that are related to our residuals. So I'm just going to use matplotlib real quick. And one thing to quickly check for is the normality assumption. So we want our residuals to be normally distributed. It's never perfectly normally distributed, but you do want it to look like this. You do want it to be centered at and around 0. So here you can see that I also did not label these. You should also definitely label these graphs. But you see here that my residuals are centered around 0, meaning that most of my error values are close to 0. And then I have some of them like plus minus 10. I have some on the high end with at like an error of 15 as well. So this is just one quick way to normality check your residual. On top of that, you have your other residual plots. And there are 2 ways to do this. And I know this looks a little bit intimidating for some people, but let me talk about what these are. So these are 2 ways that you can plot your residuals to check for homoscedasticity, as well as just checking for the predictive power of your model. And let me explain what these are in the 2 plots. So on the left side, we have the actual values of miles per gallon versus the residual. So as an example, as a really, really quick example, let me just draw it out. Let's see this data point over here, this X over here, this X being at -5 with a miles per gallon of around 11 has an error of about -5. And what that means is the actual minus predicted is -5, which is to say that the prediction was too high by 5 miles per gallon. So that's how you interpret that. Also, I don't have a mouse, so my drawing's a little bit not as good as it usually is. But anyways, here we can take a look at our homoscedasticity. Now, this is not homoscedastic at all. What we want to see for homoscedasticity is we want to see our data points looking more like this, more evenly spread out over and below this red line at 0. That would be homoscedastic. What we're seeing here is more of like, I guess what looks like a kind of parabolic nature, whereas like on the between the ranges of like 10 and 20, the errors range about here to here, and above 30, it seems like there's a lot of under prediction in our data. So our model in this case is very inconsistent, because from the ranges of about 10 through 30 miles per gallon, yes, you have like errors up and down, but above 30, you're pretty much consistently under predicting with your model, because your residual is always positive, and positive up to 15 as well. Meaning that for any car who has a miles per gallon of above 30, you're pretty much certain that your model's under predicting the miles per gallon, which is not good. That is inconsistent. You want your model to be fairly consistent at making predictions across the board. So that's one way you can interpret a residual graph like this. You want most of your values to be like pretty evenly distributed across the range of your actual values around the 0 line. Any questions about that? Okay, I think with time, actually, these are one of my favorite graphs to use for linear regression, because it kind of tells you exactly how your model is doing. Because, you know, yes, you have RMSE, but RMSE is still an aggregation, right? Because I have all of these residuals up here, that could be really biasing my RMSE to be much higher. And maybe this is a sign that I might want to cut out some of these outlier points over here. I don't know, it depends on your data as well. So that is the left side graph. Now the right side graph, same information actually, but slightly different. On the x-axis exactly the same, but on the y-axis, we have the predicted miles per gallon. And then instead, this diagonal line is actually wherever predicted and actual are equal. So basically any data point here that is along this red line is a perfect prediction. And the further you are away from the line, the higher your error value is. So this is another way to look at homoscedasticity and also at the predictive power of your model. So as you can see here, I mean, these are kind of similar shapes, just flipped different ways. But as you can sort of see here, from the range of like 30 to 35, these points are not near the red line at all. Like it seems to be following a completely different curve than this straight diagonal line, which the diagonal line again represents perfect prediction. So in this case, there is something that's just not consistent about your model, especially at the higher range of miles per gallon. And if you see something like this, what you can do is maybe you want to subset the data that your model looks at. Maybe your model will be a lot better at predicting just lower miles per gallon cars, and maybe it's not worth training this model on higher miles per gallon cars. But again, it really depends on your context, right? If your context is that you do want to be able to predict miles per gallon for the entire range of cars, then maybe you do some transformations, like maybe you log transform and see what happens there. But yeah, these are not good graphs for residuals. Questions about this? All right, again, feel free to use this code. My request is just that you understand what you're doing if you use these graphs. I have another example here using train test split. So here I'm doing my train test split. I pretty much copied and pasted the code from above, but now I have train and test, and I'm just doing the exact same graph, but with my train and test as separate colors. I should have a legend somewhere on these subplots, but I didn't do that, but please add a legend if you do decide to take this code. And basically the blue data points represent my train set and the orange represents the test set. Now what's interesting over here, as you can see, the RMSE for my test is lower than my train, which doesn't happen very often. And of course, here we only have like less than 400 data points. So sure, there's not too much data anyways. But as you can see, like through this residual plot, you can sort of explain why my test data happens to be doing better. If you just take a look at the distribution of data points over here, you'll see that on this high end, which we already know, this model is not very good at predicting the higher range of miles per gallon. On this higher end, there's just so many more blue data points compared to orange data points, right? Like in this region, there's a lot of blue data points that are further away from that zero line compared to orange data points. So naturally, you are going to get a higher RMSE for your train set than your test set just based on your train test split like this. So if you're finding results that don't make sense out of your RMSE, because RMSE is an aggregation of your error, it's really just taking an average of your error. Actually plotting your data points might illuminate why. Like maybe you have some really, really awful outliers that are throwing off your model, and through a residual plot like this, you can figure out why. Cool. And yeah, again, feel free to use this code if you'd like as well. Just don't forget to edit it such that it makes your own. Sometimes it's kind of obvious. I've seen students use this exact code and still have miles per gallon, even though their data set is not miles per gallon. So please don't forget to do that. But yeah, any questions regarding this?
Random question. Would it make sense to remove outliers before we start the regression process, or should we do that's like EDA and like actually discovering, you see that there are outliers? Is it like proper to get rid of them first and then take a look at it later, or to include them and then say, oh, well, this could be causing some noise, and then removing them?
I would say that it really depends. So that's actually something that even data scientists out in the field really struggle with. Like, first of all, what even is considered an outlier, and then also what to do about them. Because sometimes you do want to take into account your outliers, or you want to build your model to account for your outliers. And in that case, you want to keep them in because, you know, those outliers are, I guess, not really outliers, but more just like extreme values. So I would say my advice is, if you see an outlier that you know is like, this data is probably wrong, or this is like a once in a lifetime data point that's not likely to happen again, that you don't really want to account for, or you don't want to skew your data, you can get rid of it to start. However, there's different kinds of outliers also. There's outliers with regards to your target variable. So with the housing prices data set, there's a lot of outliers. There's like not a lot, but there's like a handful of houses that are like super luxury multi-million-dollar homes. And those are considered extreme values, maybe outliers in some contexts. So maybe you want to build your model to account for those, maybe you don't. However, there's also outliers on the X values within your X values. I keep using the housing data as an example, but I know that in the housing data set, there is actually one house with 33 bedrooms, which I guess I'll tell you all is probably a typo. But if it wasn't a typo, would you want to have a house that's 33 bedrooms in your data set? And also that house I know does not have a price, does not have a target value that is very extreme. So it's really up to you to make these context-based decisions. Really think about what are the implications of taking out like a group of data points that you think may or may not be relevant to the question that you're trying to answer. I would say like, if you're unsure, leave them in first and then explore things like your residual plot to figure out like whether I should take them out. Like, let's say you see here, I have like this one blue outlier. Let me like mark it out over here. I have this one blue outlier over here. And let's just say it was way further away and it's really throwing off my Rmse. What I could do is I could figure out which one this is. Several ways to go about that. I could go into my model.resid, like I can go into here, figure out which is the highest residual. So let's see, does this work? Cool. The maximum residual is 16.25 off. So I could also do there are many different ways to do this. This is not the only way, but I could sort values. And you see here that it's index number 320. I would go into my X, figure out which one is 320, and decide whether figure out whether this is an outlier that I want to account for or not. With your data, you probably will have more contextual knowledge on that, so you can make a more informed decision whether, is this an outlier that I want to get rid of, or is this like just something that does actually occur in real life that I should account for, right? I can take a look at, was it Y? Look, 320, just to see, and I don't know what these values mean because I don't know anything about cars, but if you did, you might be able to say, okay, this is an exceptionally high miles per gallon car, which is why there was like such an under prediction on the miles per gallon. So a lot of, you can get very, very like nitpicky and into the weeds when thinking about like just the topic of outliers. So for this project, I would say don't spend too much time on it, because this is something that, in your job, you can spend like weeks looking at outliers and specific values and deciding what to do with each one. So for this, I would say take a more general approach, and that should be fine.
Okay, thank you.
You're welcome. I know that's a very long-winded answer to your question.
No, it makes sense. I think I think too far ahead, and it's just like I'm gonna just like calm down, just
all good.
Just do what you gotta do on that.
All good, all good. Yeah, these are all like much shorter time frame projects than what you would do in real life anyway. So unfortunately, just because of the constraint of time, you just have to cut some processes short. Yeah. Well, I see you came off of mute.
Yeah, I wanted to, for the outliers, would it be practical or possible to sort of set parameters so that, you say, all right, I'm gonna, using housing data for an example, be like, all right, I'm only gonna look at houses that have X amount of bedrooms or X amount of bathrooms. Would that sort of, I know it would affect your data, but is that sort of a way to combat any type of outliers?
Definitely.
Models?
Yeah, definitely. It will affect your model in a sense that, when you have a more, I guess it can go, mathematically, it could go both ways. But if you are constraining extreme values, or you're setting parameters such that you don't have too many extreme values, then a lot more variation that exists can be accounted for. So typically it helps your model, and you'll see, I think in some of the example projects that some of the example presentations that I sent out, you'll see that the people who decided to look at houses like below $1 million end up with better looking assumption. I don't remember if they put their assumption graphs in their presentation, but they do end up with better looking assumption graphs, because with a smaller range of data, sometimes it's easier to achieve the assumptions, especially when it's something like housing prices, where you can go very extreme and it's not a very linear relationship between a lot of the features and the target. So yeah, that is a technique that you can definitely use.
Now, would it be better to, so, for housing, sales prices, would it be better to set parameters for the, say, all right, I'm only gonna look at houses that are valued at 5 million or less? Or would it be better to put parameters on the other features like bedrooms or lot size or lot area?
Yeah, good question. I think it's hard to say which one will be quote unquote better. It really depends on how your data is distributed. I would say start with one of them first, like start with maybe the prices first, but just know that if you were to constrict prices to, let's say I only want to predict houses below, I only want to train my model on houses below 5 million. If you ever have some sort of giant multi-million-dollar home, your model will be very, very ineffective at predicting that price, which for some contexts might be fine, right? Like if you are, let's say your business case is for like a small first-time home buyers model, then that makes sense, right? You don't need to account for those luxury homes. And usually if your scope of your model is smaller, you have more reliability on that smaller scope. You actually have a similar implication when you cut off like your outliers on your featured end as well. Like if, let's say you decide to, I'm only going to look at fewer than 4-bedroom houses, then that means that if you want to try and find the value of a home that's above, like that has like 6-7 bedrooms, your model is not going to be very reliable because it hasn't seen data like that in the data set they're using to train it. So implications like that, it's hard to say which one you do will have a better, will have a more positive impact on your metrics though.
All right, thank you.
You're welcome, but yeah, you can do both or either. Cool, anything else?
Just so I don't feel like we're taking up time, is there anything else that you
No.
want to talk about? Okay. A quick question is hypothesis testing. Like when are you supposed, like, okay, like you define your hypothesis, but when when is a proper point to say that like should you keep it general for the beginning and then reevaluate your hypothesis later on? So like as you're going, so like you set a general saying that like for like housing prices you have you believe that these some odd values may have a
significant relationship.
Yeah, significant relationship with the dependent variable. But then can you come to that conclusion and then, and this is a very general question, like this
Yeah.
is like something going on to the future, but like could you then go back and say, oh, because I was able to maybe prove that, I'm not prove, but you have your pretty
Reject
high
the null or whatever.
yeah, right.
Yeah.
Yeah, predict the null hypothesis. That you would go back into doing like those transformations, like doing the log or like doing the polynomial, like re-editing the model to then come to another conclusion.
That's
Or
okay.
would you keep it the same base hypothesis and just say, oh, I've improved my model?
That's a really interesting question. I would say it depends on what kind of approach you're running your regression under. For something like this kind of project, honestly, you don't even have to define your hypotheses because those are kind of implied when you're running your model. So you actually don't have to at any point state that I'm running this test to see whether these features have a significant relationship with the target. You actually don't have to announce that anywhere for a project like this, and in most data science projects as well. When it comes to like defining hypotheses and like picking your alpha and picking your test and all that, that's more so pure stats and like traditional stats. So I would say that if you want to do a more traditional statistics process for this project, it would be more in like your EDA, maybe you want to run like an ANOVA test to see whether I know you're doing life predicting life expectancies, right, Amir?
The
So
easier the better. I'm not trying
Yeah.
to complicate anything. So like the easier the better. But I'm
Yeah.
just kind of curious as like what, like, not for this project, but like let's say in the work environment, like what
Yeah.
like you kind of just answered it, that like you probably, like, as long as you're not like defining hypotheses, it's not like an A/B test, you have to.
yes,
But
an A/B
for
test you
this,
have to.
you
For
have to.
this,
But like for
you do
this,
not.
and like in the workplace, like could you just ignore, like, and what you said is kind of just answered it, that you really don't have to, you just implied,
Mhm.
and there it is.
Yeah,
So,
if anything, you can sort of like, not retroactively, but let's say if you want to take a more stats approach to making your conclusions, you could say, all right, let's just use this output as an example. And remember that your final model should not have any high p-values in them. But anyways, you can say, let's say you just end up with these two features, and you can say, all right, based on my model, we have found that there is a statistically significant relationship between acceleration and miles per gallon, and not acceleration, but weight and horsepower and miles per gallon. And then that's enough. Like you really only have to conclude, because the hypothesis testing is implied when you're running a linear regression.
okay, that was good.
Cool, nice. Yeah, I always forget that we went through a lot of like kind of traditional stats for like 4 weeks before we got into this.
I'm traumatized.
Oh, I was traumatized too. Don't worry. I was traumatized as well when I first went through it, and I was like, we're doing this again, and like me being traumatized from like college stats as well. And so that was, yeah, I totally get it. But yeah, anything else? All right, cool. So I'm actually going to be out of office for the rest of the week, but we have our study group on Saturday, and I'm happy to do one-on-ones on Saturday as well, before or after our study group. So please let me know if you would like a slot. My calendar doesn't show meeting times for them, but I'm going to be working that day as well. So if you want one-on-one on Saturday, more than happy to do that before or after our study group. Just let me know. Cool. Well, if there's nothing else, feel free to still reach out to me in Slack. When I'm bored, I still reply Slack messages. So feel free to reach out to me. And yeah, if there's nothing else, I will see you all on Saturday. Have a good rest of your week, everybody. Happy early birthday to Nelson. Nelson's birthday is on Friday.
Thank you. Thank you.
Happy birthday.
Happy birthday, Nelson.
All right. Have a good rest of your week. Have a good evening, guys. Bye.
Hey, Yish,
Oh,
do you want to
yeah.
hang back for a little bit? Yeah.
Yes, we will. All right, let me
Okay.
stop the recording.